Hello everyone, I'm Control Engineering Assistant. After this lecture, I will make the both English version and Korean version. Even if, although my English skill is a little bit bad, I wish that this lecture helps your work. What I'm going to talk about today is fundamental of optimal control. So I introduced the Hamilton Jacobi equation and LQR theory. Okay, let's start the presentation. Before explaining the LQR, linear quadratic regulator, Hamilton Jacobian equation is first. Hamilton Jacobian equation is derived using general form from nonlinear dynamics. There is a nonlinear dynamics, its initial value. Our final goal is find the optimal control input to minimize this cost function, where FLM is our Lipschitz continuous function. It's not input, however, Lipschitz continuous function is continuous, differentiable, and derivative value of function has upper bound. Then we define the optimal cost function, minimum value. I introduced the principle of optimality. Principle of optimality is simple. We can divide the time using t1. Then we can rewrite the equation such as this term, and then this term is the optimal cost function value with respect to t1. So we substitute this function. Finally, we can obtain this equation. This equation means solution. We can observe that from this equation, we can divide the total optimal problem to suboptimal problem, and the solution of suboptimal problem is same with total optimal solution. That is principle of optimality. And then from this equation, we reset the t1. T1 is defined as t plus delta t. Delta t is very small value. So we can rewrite the equation, substitute t1, such as we integrate this function. Integrate is find the area of trapezoid like this picture. However, we can obtain the rectangular form using this as middle value. The area of rectangular is same with the trapezoidal. So delta t product the value, some value. And then the optimal cost function can be rewritten using Taylor series and higher order term. From this value, from this equation, cancel the optimal value function and then divide the delta t. So we can get the finally Hamilton Jacobian equation. We can obtain the optimal control input u to minimize the Hamilton Jacobian equation. The optimal function is a function of the partial differential of optimal cost function. So we substitute this. We can get the PDE of optimal cost function. We should solve the PDE to get the optimal control input. However, in practice, solving this equation, solving PDE, is very difficult. So we neural network or reinforcement learning or dynamic programming to approximate the optimal solution. There is a simple example. There is sample system and the cost function. From Hamilton Jacobi equation, we can obtain this function. L is this, F is ODE this. So to minimize this function, derivative function with respect to u, we can get this equation. So optimal input can be obtained, such as substitute u bar, we can obtain the PDE. It is too hard to find this solution. However, in linear system, the solution is very trivial. There is a linear system, x dot equal ax plus bu. Our goal is saying find the optimal control input to minimize this cost function. Cost function is defined such as there is assumption, or we can define the optimal cost function x transpose px, where p is positive and symmetric. Then same procedure, Hamilton Jacobian equation, L become U transpose RU plus X transpose QX. In linear system, F is become AX plus BU. So substitute this function in here. We can get this equation. The 2x transpose P is obtained. The partial differentiable with respect to x, we rewrite this equation such as, and then to find the optimal control input to minimize this function, perfect square form with respect to control input. So plus this term minus this term. This front term can be perfect square form, and then this term becomes this equation. 2x transpose PA can be this equation. Finally, we can get the optimal control input U from perfect square form. So U optimal control input U is minus R inverse B transpose PX, where P is obtained by to minimize the second term. So second term make to 0. This equation is algebraic Riccati equation. Algebraic Riccati equation. P is obtained from this equation. We can obtain solution P using Hamiltonian matrix. However, the Matlab code is already implemented using this method. The Matlab is very simple to implement the LQR, where its important thing is that the meaning of Q and R. In cost function, R is weight of input, Q is weight of state. If you set the high value of input, if you set the high value R, the LQR control gain is selected to save the input, to consider the efficiency of input. However, the control performance is degraded. R is high, R inverse, so final control gain to become small. On the other hand, if you select the high value of Q, the control performance is improved. However, high value Q from by the high value from Q, the P obtained the large value, so the control gain becomes large. So the control input is large. The trade-off between control performance and efficiency of input. Okay, let's start to see the Matlab code. Matlab code is very simple. There is a simple system matrix, input matrix, output matrix, and then we set the weights, and we can get the control gain and P from this function, CARE. It means continuous algebraic Riccati equation. We can see the help, the compute the solution P. This is P. And finally, we can get the control gain G. Very simple. However, the procedure is not simple. We can open this function. From this function, as I mentioned, the P solved using Hamiltonian matrix process, already implemented in Matlab. So, to evaluate the performance of LQR using Simulink, blank model, set the sampling time, fixed time, solve detail. We can make the simple system and LQR controller using integral, integrator, set the initial value, in this ax plus bu, here x, so we need some a. We already defined A matrix, A using matrix product, and B, input matrix B, is X. So X dot equal AX plus BU. We designed the U using state feedback, and we can obtain the control gain using LQR function. So I set the LQR function output G using gain function. Finally, we finished the simple example of LQR. Start this simulation. We can observe that the state regulates to 0. As I mentioned, Q and R is very important. Wait a minute. If we set the Q and R is 1, the control performance and input this, the state converges to 0 at after 1 sec, and control input is used 25. To capture this picture, we reset the Q and R. As I mentioned, if the Q select the high value, the control performance is improved. However, the control input is large. You can get the new control gain, large control gain. So finally, from simulation, the states converted to 0 before 0.8 seconds. However, the control input is larger than before. Too large. However, if I set the R weight as the high value, solve the algebraic Riccati equation, we can get the small control gain. The control performance is degrade. However, the control input becomes smaller. So, I introduced the optimal control, fundamental of optimal control and LQR theory, and I implement the simple LQR example using Matlab Simulink. We can observe that the control performance and efficiency of control input is different according to set weights. Finally, we validate that the trade-off between control performance and efficiency of control input via simulation. The end of this lecture. My English is too bad. If you listen this lecture, I wish you considering this point. Thank you for watching, and please like and subscribe. Bye bye.